Hello and welcome to the first chapter in our very last unit. So we are closing down. So this is going to be chapter 18 and it is applications of the immune response. And so basically we're talking a lot about vaccination and then we have to talk about immunoassays. So as always, here are your learning objectives. So let's go ahead and get going. All right, so let's talk about the history of vaccination. There was a process called variolation, and it dates back to about 960 to 1280 in China, is the oldest record or account of this process. And so at this time, smallpox basically was throughout the world. And 1 in 3 people died of smallpox, was highly contagious. And one of the things with smallpox is people had these lesions, so they had pock marks and there was pus from those lesions. And so what they would do is they would scrape those lesions, so scrape some pus, and then they would either through inhalation, that's what's happening in this picture, this child is being variolated, or it would be placed underneath the skin. And so it was a milder disease than if someone got it, I guess, naturally. And then once someone got it, then they were immune. There was, a couple problems with this process. It was occasionally fatal. So, 1 to 2 people in 100 died. And then also during this process, since they were actually infected with the smallpox virus, which was called variola, they were also contagious. They do know that that wasn't just happening in China. This was also being performed in West Africa, Constantinople. So just other parts of the world were doing this as well. But this is the oldest record of it. So let's go ahead and get a little history lesson.
This is the smallpox virus. It infected the pharaohs, caused a terrible impact on the Greek and Roman empires, and decimated Native American populations. Nothing seemed to stop this lethal plague until the end of the 18th century. At that time, smallpox was a major global endemic disease. Only in Europe, it killed around 400,000 people per year. It didn't differentiate between rich and poor. Even 5 kings were killed. But for some reason, milkmaids and shepherdesses seemed to be immune to the disease. In fact, they were renowned for their beauty because their skins were free of the scars smallpox caused. They were attractive and resistant. But why? That's what the rural doctor Edward Jenner was trying to understand. He knew that milkmaids got small blisters on their hands when they milked cows suffering from cowpox, a mild disease that cattle suffered from, which caused similar lesions to smallpox. And this phenomenon made Jenner think that maybe cowpox and smallpox were related, and that infection with the milder disease would be enough to protect people against the lethal one. As a man of science, he decided to prove it. And to do this, he needed 3 things. Cowpox that he extracted from a milkmaid, fresh smallpox from a patient, and a human guinea pig. He chose his gardener's son, an 8-year-old boy called James Phipps. He infected the child with cowpox, waited a couple of months, and injected him with smallpox. And James didn't become ill. He repeated the experiment with other patients with the same results. Jenner was right, even though he didn't fully understand how his remedy worked. The most remarkable thing was that his discoveries were made way before Jacob Henle proposed in 1840 that infectious diseases were caused by germs, a theory demonstrated by Robert Koch. Decades later, Louis Pasteur, inspired by Jenner's experiments, showed that attenuated microbes could be used to prevent diseases, and he proposed the terminus vaccine in his honor. Almost 200 years after Jenner's experiments, and thanks to global vaccination campaigns, in 1980, the World Health Organization announced one of humanity's biggest achievements, the complete eradication of smallpox, the most deadly infectious disease in history.
So that was just a nice bit of history there. Yeah, can you imagine just being the gardener and going, hey, can I use your son? I'd like to perform an experiment on him. Hopefully he was compensated, or maybe that gardener just had great faith in Jenner. But that's just a great piece of history, and well before the germ theory, which is pretty amazing. Okay, so Pasteur, that's where we got that word vaccination in honor of Jenner and his use of cowpox. Louis Pasteur, he was working on anthrax and rabies. But vaccination is deliberately stimulating the immune system through protective inoculation. So as we've been going through this semester, we just finished off the immune wars. So we talked about the immune system. We had already previously talked about the different types of pathogens, so bacteria and protists and helminths and viruses, and how they fight back and how they cause disease by basically attaching, colonizing, and causing damage. And so this last unit is the return of the humans. So knowledge is power. And so we're talking about immunization, epidemiology, and then some antimicrobial medications, and then we will be done. So just to get you in the mood. All right, hope you're pumped. Okay, so let's look at immunization. So immunization is the process of inducing immunity. And we say that someone has immunity. It means that they can become exposed to a particular pathogen, yet they won't get the disease. And so immunization has probably had the greatest impact on human health above any other medical procedure. And so there's different types of immunity, and it's always going to be a combination of two words. And so the first part is always going to say whether that immunity was through a natural course of events, meaning not a healthcare worker was not involved in any way, shape, or form, or did someone gain immunity through artificial events, so through immunization. So basically, yes, though in some way healthcare was involved. The other word that's going to be used in combination with either natural or artificial is either going to be active or passive. And so if someone has active immunity, it means that their own lymphocytes were exposed to the antigen, their lymphocytes responded, they were activated, and they now have memory cells, and therefore they have immunity. So active immunity is going to last the course of a lifetime, or at least as long as someone has those memory lymphocytes. So our immune system, it gets better as we grow up, and then in adulthood it's good, and then it does kind of wane as we age because some of those memory cells die. But for the most part, that immunity can last for a lifetime. The other type of immunity is going to be passive immunity. And so that word, you kind of, implies there's no activity there. And that means that that person's immune system did not mount the response, meaning those antibodies were borrowed. And so this person, since they were never responding to an antigen, they do not have memory. So passive immunity, the big thing you need to remember about that is it's temporary immunity. It's only going to last as long as those antibodies are in someone's body. Okay, so let's look at some examples. All right, so you got sick, you got better, you are now immune. What type of immunity? So the first part of that immunity is either going to be natural or artificial. And so just getting sick, that is just a natural course of events. This is going to be natural immunity. The second part of the word we want to know, is it active immunity or is it passive immunity? And in this case, that person got sick, which is you got better, and you are now immune. So that means your lymphocytes were activated. They responded to the antigen. You now have memory cells, so probably memory B cells, memory T cells, and so you now have immunity. So it's going to be natural, active immunity is the type of immunity someone has when they get sick. All right, let's see if you can do the next one without me. All right, so you get your meningitis shot. What type of immunity? So you were vaccinated for meningitis. So is that natural or artificial? So no healthcare worker. And then through vaccination, does a person have active immunity, meaning their body responded and they'll have memory? Or was it passive? Were there antibodies given? Okay, let's see if you can do the next one. A mother breastfeeds her child. IgA, so secretory IgA, those are those dimers that protect the mucosa. So IgA antibodies are transferred, offering disease resistance. What type of immunity does that child now have? Was this a natural event or was this an artificial event? Has that baby immune system been activated and generated the response, or are these antibodies borrowed? All right, back to the babies again. Oh, a baby is being treated for botulism. So the causative agent, Clostridium botulinum, spore forming. So maybe this mother didn't know and she gave her baby some honey, and now that we've got a floppy baby. And so if that were the case, that baby would be given botulism, immunoglobulin intravenously. So they call it big IV. So they basically be given an antitoxin. What type of immunity is this? Is it through a natural course of events or artificial? Would this baby have active immunity or passive immunity? Okay, hopefully you got all of those. All right, so this is just a picture from your books. So remember, natural active immunity is immunity that results from an immune response in an individual after exposure to infectious agents. You can get it naturally through just the course of getting sick or through vaccination. Either way, with active immunity, it's long lasting, and that person's own body has memory cells. So memory B cells, memory T cells. And so that memory is going to last. That immunity is going to last. Over here, so passive immunity, we talked about natural passive immunity. This happens through a mother to her fetus. So during pregnancy, those IgG antibodies can cross the placenta. And so these are soluble antibodies. And so when the baby is born, that baby is going to have IgG antibodies from their mother. And so that's going to be natural because, no healthcare worker, passive immunity. Also, if that mother continues to breastfeed, there is secretory IgA in colostrum and also in breast milk. So that's going to protect the baby's intestinal lining. So this is an example of natural passive immunity. There will be no memory. It's going to be temporary. Those IgG antibodies from inner utero, they're going to be lost slowly, gradually over time. And then two, once that mother stops breastfeeding, then that baby's no longer getting that IgA protection of the mucosa. So let's look at artificial passive immunity. This immunity that results when antibodies contained in serum of other people or animals are injected into an individual. So this would be immunoglobulins like IgG. This could be used to treat unvaccinated people who have been recently exposed to certain diseases, hepatitis A, measles. If there is someone who is immunosuppressed and they've been exposed, they also might be given artificial passive immunity, so immunoglobulins. So this is when we were talking about antibody therapy. This would be another example of that. It is artificial and it is passive. That passivity, that means this is going to be temporary. There will be no memory. And once again, it's only going to last as long as those antibodies remain in the body. So there we go. So injection of antiserum containing antibodies can prevent disease before or after likely exposure, limit the duration of certain diseases. So that's that antibody therapy to sort of help someone get better more quickly, and then block the action of microbial toxins. A lot of times when antitoxins are given, so think of in tetanus, in botulism, in diphtheria, what you're doing is you're giving somebody time and reducing the amount of damage that that toxin is causing, because it takes time for the body to mount an immune response. So these antibodies are given to neutralize those toxins and target them for destruction. There's two types of antiserum. There's something called hyperimmunoglobulin. So that would be like that tetanus immunoglobulin, rabies immunoglobulin, hepatitis B immunoglobulin. So this would be specific for particular disease or toxins. Sometimes though, when people are immunosuppressed for one reason or another, going through cancer treatment, or they have a immunodeficiency, just be pooled serum. So IgG fraction from many donors, which if you think about it, people out and about with this healthy immune system, they're going to be making a variety of antibodies at any one given time. But just once again, this is going to be artificial. So, and then passive immunity. So only as long as those antibodies are in that system. So vaccination, so we're going to talk about different types of vaccines. A vaccine is a preparation of a pathogen or its products that's used to induce active immunity. And it's to protect the individual that's getting vaccinated, but it also prevents the spread of that disease in population. We're going to talk about something, herd immunity, and you probably heard a lot about it on the news. Herd immunity develops when a critical portion of a population is immune to a particular disease. And so it basically restricts the spread of a disease because there's not enough susceptible hosts. This is responsible for the dramatic declines in childhood diseases. And then sometimes, though, if people fail to vaccinate, then we lose that herd immunity. And I think it'll be a little easier. I have a YouTube for you.
Most people are familiar with vaccines and how they offer individual immunity against a disease, but they might not understand how the people around us or our herd offers immunity to everyone in the herd. A herd is a group of mammals that are living together for protection, maybe protection against lions in Africa or wolves in North America, but how does that apply to humans and disease? Well, let me show you a little model I put together. So we have these individuals in a herd, and let's say one of them gets sick, and the infection rate of this disease is 50%. There's a 50% chance you could pass that on to another individual. So this person is in close contact with 1, 2, 3 individuals, and so I simply flipped a coin. Heads you get sick, tails you don't, and 2 of the people got sick. I then took those individuals and flipped coins for the people around them, and this person, for example, infected 1 individual, and this person infected 2. And then I just kept doing that over and over and over, and you can see how the disease spread through the population. Now, how quickly a disease spreads through a population is based on how many people you can infect, and we call this the basic reproduction number. What is that? Well, for this individual, they infected 2. This person infected 1, this person infected 2, this person infected 0, and if I take a number of those individuals and find their average, that's going to be my basic reproduction number, or R naught. If R naught is ever less than 1, in other words, you can infect at least one other person, then the disease dies out. But if you've ever heard of a disease, that means its R naught value is going to be greater than 1. And so here's some R naught values for some diseases you might be familiar with. So the recent outbreak of Ebola, R naught value 1.5 to 2.5, smallpox 5 to 7, but some diseases like measles and whooping cough, the R naught value might be as great as 18. That's because it's an airborne transmission. And so what happens after you get a disease? Well, you get sick, and in some diseases you might even die. But if you know anything about animals, we can gain immunity to that disease. Once we've got the disease, we're not going to get the same disease again unless it mutates highly. And so what these people with immunity do is they offer protection to everyone else within the herd. So let's see that disease comes in again, and it starts to spread through a certain part of the population. Well, the rest of the population can't get it because these people with immunity offer a fire break or a firewall against that disease spreading into the population. And so once our herd gets large enough, like this, even though a lot of people don't have individual immunity, they have herd immunity. So let's say a person like this comes in who's sick. They're surrounded by so many individuals who are immune that the disease can't spread to those who are susceptible. And so the problem with this is you have to get sick, or you have to have members of your population die for you to get this herd immunity. But science has come up with a solution to that. It's called the vaccine. We give you a weakened or a dead version of that disease, and then you can gain immunity to it. And so that's wonderful. And you might think, let's go back to that model again. Let's simply vaccinate everybody. If we vaccinate everybody, everybody has immunity. But we can't vaccinate everybody because it's a voluntary process to get vaccinated. Some people don't want to. You shouldn't get like a measles vaccine if you're a baby or you're a pregnant female. And then as you get older, you may lose some of this immunity. So not everybody can be vaccinated. It just simply doesn't work that way. And so what scientists have come up with is a herd immunity threshold. What does that mean? It's how good is good enough? What percent of our population do we have to have vaccinated or immune to the disease so we all get this herd immunity? Well, it's going to depend on the R naught value of the disease. So if it's something like mumps with an R naught value of 4 to 7, we have to have at least 75 to 86% of the population who is immune, so the whole herd can gain immunity. But as those R naught values get greater and greater and greater, like 18 in measles, we have to have 94% of the individuals immune. And so as people decide not to get vaccinated, what's going to happen? We lose that herd immunity, and we're going to have outbreaks of disease. So if you live on the plains of Africa, you're protected in a herd against a predator like a lion, but who is the lion that's stalking us? It's the disease, which is hiding in other individuals around us, but we also now have to worry about the individuals around us. Are they immune? Are they vaccinated? If not, they're not only putting themselves at risk, but they're putting the whole herd at risk.
Okay, so let's talk about that vaccination and herd immunity. So we just looked at some R naught values. And so the R naught values, two of the biggies that were basically eradicated through immunization. We'll look at some stats in just a minute. Measles and pertussis. And I'm sure you've heard of the anti-vaxxer movement. And so we've had outbreaks of both measles and pertussis, just because in order to maintain that herd immunity, we need to keep approximately 94% of our populace vaccinated, and that's not what's happening anymore. And so we've had these outbreaks, and yes, Texas is one of those states with measles outbreaks. We've had some outbreaks in Montgomery County and other counties as well. And so this is off the CDC. U.S. measles cases in first 5 months of 2019 surpassed the total cases per year for the past 25 years. And like I said, it doesn't take that many people to not get vaccinated. And it really is to protect those that can't get vaccinated. So very young children, pregnant mothers. Some vaccines don't work if someone is immunocompromised. They can't have those vaccines. And then two, as the populace ages, we know that they become immunocompromised. And so you don't really know when they lose that immunity. So it is really important for people to get vaccinated. And measles was something almost every kid got back in time before that vaccination came up. And it can be fatal. Even now with treatment, 0.2% in the US populace contract measles, die. All right, so I'm going to give you this table, and so we're going to talk about the different types of vaccines. And so once again, it's a great table to study from. It's all there, but it's horrible to teach from. There's not a whole lot to look at. So I'll give you that to study from, but we're going to look at this. So if you think about a good vaccine, its goal is to give long-lasting protection. So that vaccine has to be something that's immunogenic, and it's really going to stimulate the immune system to create those memory cells. It also needs to be safe with few side effects. We don't want it to be toxic, obviously. Ideally, it's going to be something that's cheap, easy to administer, and then two, if you think about the global aspect of it, something that's stable, that doesn't require refrigeration, that doesn't have a short half-life. And so there's two basic groups of vaccines. There's what's called an attenuated vaccine, and this is a vaccine that's basically, it's a weakened form of a live pathogen. So back to the history, the cowpox virus was basically an attenuated type of vaccine. It was something that was living, and the big thing about it that's going to make up the differences that we're going to look at, if something is living, that means it can replicate. And so the immune system can be exposed to a lot of that antigen. The other type, and it's a very big group, well, there's a lot of different types in this, are called an inactivated vaccine. And since they're inactivated, they're not living. I know viruses are technically not alive, but I'm just saying this is something that it's a vaccine that is unable to replicate. So only the dosage, if you will, or the amount of agent that's in the vaccine, that's all the body's going to see. And so they each have pros and cons. And so when we're looking at an attenuated vaccine, so think about this as the weakened strain, the pros of it is that attenuated vaccines are very good vaccines, meaning they really do stimulate the immune system. We're going to have both cell-mediated and humoral immunity. The other thing about them, since they are living and they can replicate, a single dosage usually does it. So it doesn't require repeated introduction to that antigen. Another pro to an attenuated vaccine, since this is something living, there's also what's called inadvertent immunization. So someone gets their vaccination, they could inadvertently spread this weakened strain to another person, so therefore they would basically be immunized. So secondhand immunization, if you want to think about it that way. Also, attenuated vaccines, the administration can be through an injection. Some of them can be oral, and some of them can also be nasal. The downside to an attenuated vaccine is it's not safe for everyone, since this is a living form or a pathogen that can replicate. So pregnant women shouldn't get it, very small infants shouldn't get it. And then the other thing is it may cause disease in immunosuppressed people. So, like I said, it's not for everyone. The other downside is it can revert or mutate back into a pathogenic strain. Usually, too, these require refrigeration. If we pop over here, so remember the inactivated vaccines, they are unable to replicate. The pros is it cannot cause infection or revert back to pathogenic form, so they're very, very, very safe. So there's no risk to immunocompromise. They can be given to everybody. And usually they're more stable. So something that would be more stable, once again, thinking globally, if like World Health Organization, when they go to third world countries and stuff, it would be an easier vaccine to transport. The downside, shorter duration of protection. Since it is unable to replicate, you're not going to get as great of an immune response. Several boosters are normally needed, and usually, once again, since this is not reproducing inside the body, you're not going to get that cell-mediated immunity, so that's going to be poor. The other thing, it has to be administered through injection, and people don't like to get shots. So how are these made? So an attenuated vaccine, remember it's a weakened form of a live pathogen. Usually how that's going to occur, it's going to be grown under conditions that are going to foster mutations. And a lot of time what this involves is just passing through different types of cell lines, growing them in different medias and things like that will achieve this. Or they can be genetically manipulated to replace those genes. The big thing is that these are going to have a lower pathogenicity, so very weakened. And so the big example I want you to remember is the MMRV, because it's one that's given. This is against measles, mumps, rubella, and then the varicella zoster virus chickenpox. And so they are usually given together. There's also attenuated vaccines for rotavirus and yellow fever. Over here, this inactivated group, it's a big group. We're going to look at all the different types. The big thing is, once again, it's unable to replicate. So what they're going to do is they're going to either destroy or make sure that this inactivated vaccine doesn't contain the toxic part. But the big thing, in order for it to be immunogenic and give protection, it has to keep the epitopes. So it has to keep those antigenic determinants. A lot of times, too, since we're just taking little pieces, parts, they're small. And in order to make them immunogenic enough, they have to be used with what's called an adjuvant. And so an adjuvant is a substance that helps induce a better immune response. The downside of these is sometimes people have reactions to that adjuvant. And a really common one is alum, and so it's aluminum based, and so people have reactions to it. They are now making a lipid A adjuvant, so using that endotoxin from gram negatives to act as that adjuvant, so it would be more of a natural response. Examples of inactivated vaccines, and there's a whole bunch of them, but I said if you could just kind of collectively go the H's. So Hib vaccine, so Haemophilus influenza B, which caused that meningitis in young children, hepatitis B, HPV, so human papillomavirus, and then that toxoid vaccine, so DTaP, so diphtheria, tetanus, and pertussis. So we'll be looking at those. All right, so from now on, attenuated vaccines, it's just a weakened strain. But when we go inactivated, so basically we are going to kill things, but you can have an inactivated whole agent vaccine. So either killed bacteria or an inactivated virus. And so you would just take that and you would treat it usually with formalin, or there's other chemicals, and it kills it, so it's not going to replicate, but it doesn't change the surface epitopes. I'm recording this at the end of April, and so trials for a vaccine for SARS-CoV-2 are going on in China, and they just took the virus and they just treated it with formalin. And so just quick and dirty, kind of an easy way to create a vaccine. Things that are currently being used is what we use for rabies and hepatitis A. We've talked about toxins and their damage and how toxoids are a not harmful version of that toxin, but once again, it's going to retain its antigenic epitopes. And so we have antitoxin for diphtheria, tetanus. We just talked about botulism. And like I said, the big thing with if you have a vaccine against that toxin, even if someone's exposed, it's going to basically neutralize that toxin, give them time to reduce that damage, and then the body can have an immune response to the actual agent that's causing or making that toxin. The subunit vaccines, kind of what it sounds like, so subunit, so just a piece of the whole. So we're going to have key protein antigens or antigenic fragments from a pathogen. And this just avoids cell parts that may cause particular side effects. Acellular pertussis vaccine, because the whole cell, the inactivated whole agent actually caused side effects. And so that would just be a reason someone would use a subunit vaccine. Other types of vaccines, so recombinant subunit vaccines, and this would just be made through genetic engineering. So for hepatitis B virus, what they did is they took those antigenic outer proteins and had spike proteins and had them produced by yeast cells. You can also do the same thing by just injecting someone with a virus-like particle, and that's just that empty capsid, so no genetic information inside. So that can't possibly cause disease. So that's an example, that Gardasil against human papillomavirus in hopes of eradicating cervical cancer. Human papillomavirus, remember, causes genital warts. There's also what's called a polysaccharide vaccine, so many sugars. So it contains polysaccharides from capsules. These are going to be T-independent antigens. So this isn't a vaccine you would use in young children because there'd be a poor response, but it works perfectly well in adults. So that pneumococcal vaccine against pneumonia, that's advised for patients 50 years of age and older. And so it just has the polysaccharide vaccine. Usually that's a capsule against 23 different serotypes. Conjugate vaccines, so polysaccharides linked to proteins. So conjugate, two things linked together. And so when you do that, if you link proteins to those polysaccharides, that converts a T-independent antigen into a T-dependent antigen, so it can be used for children. So that's how they got the Haemophilus influenza type B, that Hib vaccine. Like I said, that was that #1. We watched YouTube about it, caused meningitis in children. This is also what's being used for Streptococcus pneumoniae. So just other ones, so conjugate vaccines, putting two things together. And this is kind of interesting. I actually had a note about this. So the nucleic acid-based vaccines. And so what they've realized that they can take segments of naked DNA or RNA from infectious agents, so coding for a protein, and so they would inject it, and for a short time, the host cell or the recipient of that vaccine would actually express that antigen. And so that antigen expressed then, of course, would induce immune response, but evidently that is an area of research. So importance of vaccines. So this is just kind of showing you effectiveness of universal immunization. And so after immunization, we've reduced the number of diphtheria, Haemophilus influenza type B, 98.8, measles, except for those outbreaks, nearly 100%, mumps, whooping cough, polio, rubella, smallpox, tetanus, so all of those things. So the benefits to vaccination greatly outweigh the slight risks. And so children with measles has a 1 in 2,000 chance of serious brain inflammation versus a 1 in a million chance of having a reaction to that vaccine. And so just prior to vaccination, a lot of these diseases too came with disabilities. So why do we still have them? Like I said, not to trash people. People are doing what they think is best. But vaccines have basically become victims of their own success. People haven't witnessed or seen these diseases, and they don't know the repercussions of getting these diseases. So a lot of these lead to neurological issues. Polio leads to paralysis. And so no one's ever seen these diseases before. Another thing, some parents refuse to vaccinate children for fear of harm. There is no evidence of link between vaccines and autism. That was a study. The man basically that wrote it, the lead doctor, he fabricated his data. He lied. Long and short of it. It was picked up by celebrities and then publicized, and everyone believed it. Reports of adverse effects of vaccine have led some to falsely believe the risk of vaccination is greater than the risk of disease. And that's part of that. No one remembers what those diseases did, and no one knows. And so there's a whole lot of chatter on there. Yeah. You are the educated. So the CDC publishes recommended schedule for routine immunizations, and I certainly don't expect you to memorize any of these. But we know that bacterial diseases have been prevented by routine vaccination. So, this is kind of like a good little review for us. And so we have diphtheria, which we kind of talked about that one already. So Corynebacterium diphtheriae, that was that gram-positive rod. We looked about the whole Balto thing and that antitoxin. Haemophilus influenza B, and that was that bacterial disease that caused that fatal meningitis in children under 5. Meningococcal, that was the Neisseria meningitidis. That's the one that you received. And then Bordetella pertussis, that causes whooping cough. And then Streptococcus pneumoniae, so that pneumococcal disease. And that polysaccharide one, that's going to just be for adults. Okay, over 65. I knew it was for older people. And then Clostridium tetani, that causes tetanus. And so that's that toxoid vaccine. And so we've kind of discussed a lot of those. Okay, we just kind of wrapped up our viral unit as well. So we know the hepatitis that causes liver cancer and liver disease, human papillomavirus, which is linked to cervical cancer. Influenza, we know that is a virus that goes through antigenic drift and antigenic shift. Measles, mumps, we talked about those. Polio, we're about to. Rotavirus, rubella, German measles, that could actually cause miscarriages if a woman's never been exposed to that before. That's not something we want to drop. Shingles, we talked about that. That's that booster for that varicella zoster, so the same virus that causes chickenpox. There are also some non-routine vaccines. So this would be in special cases. So if someone's in the military, they're traveling to a particular place, they work with the animals, they would get some of these vaccines as well. All right, so I think we're going to wrap up campaign to eliminate polio. So polio is caused by a virus, and there's 3 different serotypes. It's going to enter via the mouth. And this was a disease that it was a summer disease. It would strike children. And so it would go from the throat to the intestinal tract and then would invade into the bloodstream. When it got to the bloodstream, it could invade nerve cells and cause paralysis. It mainly affected small children, so under the age of 5. According to the stats from WHO, 1 in 200 infections would lead to irreversible paralysis. From those that were paralyzed, about 5 to 10% would die because the diaphragm would also get paralyzed, so they put them in those iron lung machines. I'll let you Google that. Cases due to wild poliovirus, they decreased because there was just a global effort to get rid of polio. And so over 99% since 1988. So we went from a whole bunch of cases, so 350,000 to 33 reported cases. So how did we get there? Okay, so once again, we're going to get a little history lesson and look at that campaign to eliminate polio. So there was 2 men, so Dr. Jonas Salk and Albert Sabin. And Salk came up with a vaccine, and it was an inactivated virus, so IPV. And so this is one, remember, it's unable to replicate. So the pros of this vaccine were it was licensed first, and it did dramatically lower the rate of polio. So the cons to the Salk inactivated virus is that it required a series of injections for maximum protection. The other problem too is when someone is exposed to the wild type, once it gets to the bloodstream, they have protection, but that virus can still replicate while it's in the gastrointestinal tract and be shed in the feces. So transmission was still possible. Over here, so Albert Sabin, he attenuated his vaccine, and so oral polio vaccine. So IPV is inactivated, OPV is an oral vaccine, and so it was a weakened form of live pathogen that can replicate. The pros to that is it was cheaper. It could also be given through oral administration, so kids are kind of okay with that. Some adults don't like shots either. And then it gave a better IgA and an IgG response. And so that means if someone was exposed to it, they would not be infectious like over here. And so this was better for giving herd immunity. The cons of it, since it was an attenuated virus, is that it could mutate. And about 1 in 2.4 million doses resulted in poliomyelitis, so the disease where it infects the nervous system. So through that oral polio vaccine, that's actually what was used to eliminate polio from the United States in 1980. Since it has pretty much been eradicated in the United States, this worry of someone getting the IPV, which is safer, there's no reversion because it is an inactivated virus, we have switched to only giving the IPV. And so that's what's given, it's injected, 4 doses are recommended. And so this is the kind of story, I know if you are reading your textbook, they kind of give you the whole, oh, they gave the IPV first and the OPV. That is not the story I've learned. I did a little research, not truly extensive. I don't really know where they're getting that from. So we're just going to kind of go with this. And this was just kind of a story about the 2 different types of vaccines. And so remember, inactivated, unable to replicate, you need multiple shots, but it is safer. OPV, since it's one with an attenuated vaccine, it is live, it can replicate, it gave great immunity. Dangers are that an attenuated virus can also mutate and go back and revert and cause disease. And so OPV is what we use to eliminate it, and now that is no longer used in the United States, so it's IPV because it's safer and there is no chance of reversion. All right, so I'm going to wrap it up there, and we'll come back for part 2 and discuss immunoassays. Have an awesome day.